To conclude section 1.7, we're going to talk about absolute value inequalities. This video essentially covers two main cases. Let A be some algebraic expression, and let C be a positive real number. The first case is when the absolute value of A is less than C. Suppose we had absolute value of x was less than 4. Then just by trial and error, we can see that values of 1, -2, -3.5, and so on satisfy this inequality. However, values that are too big, like 5 or -4 or 6, don't work. So the intuition here is that when absolute value of stuff is less than a number, then everything inside that absolute value is essentially trapped between the positive and negative version of that number outside. Let's draw this on a number line. The absolute value of x less than 4, or the solutions therein, can be sketched as all real numbers between -4 and +4. So this amounts to solving the compound inequality -4 less than x less than 4. Again, to convince us that this makes sense, values of x like 1, -2, -3.5 live between these endpoints and they satisfy the absolute value inequality. But any value that's too large in magnitude, which falls outside of that line segment, will not satisfy the inequality. So the general rule goes as follows. If the absolute value of A is less than a positive number C, then we'll solve the compound inequality -C less than A less than C. For our first example, we'll solve 2 times absolute value of 3y plus 1 minus 3 is less than 5. First, we need to isolate the absolute value term like we've done in previous examples. By adding a 3 to both sides, we get 2 times absolute value of 3y plus 1 is less than or equal to 8, and then dividing both sides by positive 2 gives absolute value of 3y plus 1 is less than or equal to 4. And now that this is in the prescribed form, we can split this up into the following compound inequality. We'll get -4 is less than or equal to 3y plus 1 is less than or equal to +4. Note that my original problem started with a weak inequality, so I'll use two weak inequalities to trap 3y plus 1 in between plus and minus 4. At this point, I just need to isolate y in the middle, so I'll subtract 1 from both sides, then divide by 3, and I'll get the final solution set of the interval from -5/3 to 1 included on both sides. So this is case 1. If absolute value of stuff is less than a number, then I get the kind of compound inequality where that quantity is trapped between the positive and negative version of the number outside. For our next example, we're going to solve for z. 2 times absolute value of 5 minus z minus 12 is less than 0. Just like before, I need to isolate the absolute value term. I'll start by adding a 12 to both sides, and then I'll divide both sides by 2 to get the absolute value of 5 minus z is less than 6. This is in the form that I want, so I can go ahead and split this into a compound inequality. I'll get -6 is less than 5 minus z is less than +6. Next, I'll subtract a 5 from all sides, so I'll have -11 less than -z less than 1. Then I'll divide everything by a -1, and that's going to flip all my inequalities and change all my signs. And then, like I always do, I'm going to rotate this so that my negative numbers are on the left and my positive numbers are on the right. Again, that second to the last step, I haven't actually changed or flipped inequalities. I have just reflected this, but the statements are mathematically the same. Next, we can sketch our solution set on the number line so that we can see that the solution set itself is the interval from -1 to 11, open at both ends. Is there a case where something can go wrong? Suppose I have the absolute value of 2x minus 1 plus 2 is less than 1. Subtracting a 2 from both sides gives me absolute value of 2x minus 1 is less than -1. This is going to have no solutions because nothing inside that absolute value will ever produce a negative number. So if ever we encounter this situation where absolute value of stuff is less than 0 or a negative value, there will be no solution. Now we're going to look at case 2. Suppose that the absolute value of A is now bigger than a number C. Well, like before, let's consider the inequality absolute value of x greater than 4. Numbers like 5 and -6 now work, but numbers like 0, 1, and -2 don't work. I've essentially turned my situation inside out. So let's sketch this out. The inequality absolute value of x greater than 4 has a solution set of numbers that are either less than -4 or larger than +4. So by changing the direction of the inequality, I've essentially inverted my solution set. So instead of -4 less than x less than +4 like we had last time, I now either have x is less than -4 or x is bigger than +4, this other kind of compound inequality that we can get. Again, numbers like 5 or -6 or -7 satisfy this inequality, whereas numbers like 0, 1, and -2 don't. In general, if the absolute value of a is bigger than a number c, then we're going to solve both the equations a less than -c or a greater than +c. It might seem strange that we're saying both and or at the same time, but again, this is just a formality on phrasing. We are solving both inequalities. Let's jump right into an example. We want to solve the inequality absolute value of 3x plus 2 is strictly bigger than 7. The absolute value of stuff is bigger than 7, so we're going to set up two inequalities. 3x plus 2 is less than -7, or 3x plus 2 is greater than +7. Solving both of these happens pretty quickly, and we'll get the solutions of x less than -9 or x greater than 5/3. At this point, we can sketch a number line and display our solution. So this is case 2, and it still amounts to solving a compound inequality, essentially like case 1. We more or less just have an inversion of case 1 here. Next, suppose that we're going to solve the inequality 2 times absolute value of 3y minus 2 plus 4 is greater than absolute value of 3y minus 2 plus 11. It seems like I'm throwing a curveball at y'all, but I promise you I'm not. Notice that the two absolute value quantities on either side are actually exactly the same. We can essentially combine them by subtracting absolute value of 3y minus 2 from the right, putting it on the left. More or less, we're playing a game of combining like terms. So 2 copies of this absolute value minus 1 identical copy is going to give us the inequality absolute value of 3y minus 2 plus 4 is greater than 11. Next, let's subtract that 4 from both sides to put things into the desired form. I'm going to get absolute value of 3y minus 2 is strictly bigger than 7. At this point, I'm in a case 2 situation, so I can split. I'm going to get the following inequalities. 3y minus 2 is less than -7, or 3y minus 2 is bigger than +7. Solving that first inequality yields a solution of y less than -5/3. And the second inequality solves with a solution of y bigger than +3. Sketching this on a number line and plotting our interval is going to give us our final solution set. So this pretty much encompasses the cases that we're going to see with absolute value inequalities. I'm either in case 1 or case 2 as we've presented it. And really the curveball with this problem is that even though I had 2 inequalities, they were the exact same inequalities. So I can more or less combine them as if I was combining like terms.